Hello, today we are making a presentation for multi-agent motion planning for non-holonomic mobile robots via heuristic optimization. Team members are Vishrut Bohara, myself Aadesh Varude and Gaikwad. The first of all, we'll look up to the research problem and its descriptions. The problem under consideration is a motion planning approach that generates safe, dynamically feasible and near optimal trajectories for multiple non-holonomic mobile robots. The state-of-the-art motion planning approach divides the path search of the agents based on priority. However, prioritized optimization may lead to infeasible subproblems for lower priority robots due to lack of consideration by the higher priority robots. Hence, we propose a heuristic-based approach that highlights the non-optimality of the state-of-the-art approach. We'll look at the application impacts. As one can infer from the slides, the multi-agent robots can be used in sync for execution of various intricate tasks in warehouse. This coordinated approach allows the robot to work together effectively and efficiently. Moreover, the fleet of robots can be utilized for surveillance purposes. In addition to these applications, multi-agent path planning can leverage the search and rescue operations, particularly in the area that are hard to reach and dangerous for humans. The use of multiple robots can prove effectiveness of the search and rescue missions, allowing for wider coverage of the area and potentially leading to a faster discovery of the survivors. Hence, multi-agent path planning is crucial. Now we'll quickly glance over the literature review. The first paper that we have here, and which is the state of the art for the current implementation, is efficient trajectory planning for multiple non-holonomic mobile robots via prioritized trajectory optimization. The author proposes a threefold solution. The first step is an efficient trajectory planning approach for implementing a feasible and collision-free path in the environment. Secondly, a safe corridor is created and prioritized trajectory planning method is implemented to solve multiple robot planning problem and increase computational efficiency. In the last step, the trajectories are smoothened and the testing is done on multiple agents. Further, we review suboptimal variants of conflict-based search algorithms for multiple agent pathfinding problem. This paper proposes several modifications to conflict-based search algorithms to improve its runtime performance while still maintaining the near optimal solutions for multi-agent pathfinding. These three algorithms are greedy search-based search. Then the BCBS variant applies focal search to both levels of CBS and using different heuristics. Then we have the efficient based CBS algorithm that generates a CT node and a lower level search returns two values to the high level search and the cost of the node and the minimum lower bound of all the nodes in the open list of the high level search. Further, we review the RISC DT RRT based optimal motion planning algorithm for mobile robots. This paper proposes a computationally efficient optimization approach of mobile robots. The proposed method first calculates a path using RRT algorithm, which is then optimized using line of sight control checking algorithm. The author also proves that this algorithm returns a homotopy optimal path. This algorithm is less expensive in terms of computation and can be used for multi-agent systems. Further, I will hand over the slides to Om to present further.
So, for our project, we have implemented the following algorithms. One is a priority-based algorithm having CBS using line-of-sight approach and CBS using motion primitives. The second approach is heuristic-based, containing online CBS using motion primitives. Our first implementation is CBS using LOS approach. This is a priority-based algorithm in which the first A-star path is calculated using CBS with prior robot's path. The calculated paths are then smoothed and optimized in the safety set to follow non-holonomic constraints. LOS optimization was used instead of MPC optimization as it is proven to return homotopy optimal path and is less computationally expensive than MPC. For our next algorithm, we integrate the conflict-based A-star search with motion primitives that are preferred considering non-holonomic constraints. For each node, the algorithm chooses an action from the set of motion primitives and validates those actions for collision avoidance and boundary conditions. This path search is computed in a priority order and then The computed paths of high priority robots are considered as collision points in CBS to ensure safe collision-free trajectories. For the heuristic-based implementation, we created an online CBS algorithm which also uses motion primitives. This algorithm first decomposes the configuration space into discrete set. Then, for each agent, it calculates the path cost of all discrete points in the set to the goal using BFS and defined motion primitives, as it can be seen in the first for loop from the pseudocode on the right. After that, all agents greedily follow the path which minimizes the sum of BFS cost and distance heuristic with all the robots.
Now we present the preliminary results for the implementation without non-holonomic constraints for 2, 4 and 6 agents. As observed from the visualizer, the agent maneuver in the environment from a given start point to a goal point without colliding with obstacles and other agents. Next, we present the results for our implementation with non-holonomic constraints for 2, 4 and 6 agents. As observed here, the agent follows a non-holonomic trajectory from start point to a goal point without colliding with obstacles and other agents. Next, we have the results for the trajectory generated by novel heuristic based algorithm for 3 and 4 non-holonomic robots in an empty grid environment. As evident from the figure, all the agents take equivalent amount of time as opposed to the priority based implementation as seen in previous slides. For the simulation testing, we chose Argos as our platform. Argos is a multi-physics robot simulator which can simulate large-scale swarm of robots of any kind efficiently. The reason for our choice is Argos is faster than Gazebo, it has modularity, it is scalable, and it gives us a functionality of behavior-based approach in which we can program all the robots to follow the same controller. Overall, Argos is a great choice for swarm robotic research. Next, we present the implementation of priority-based algorithm for 3 agents in an Argos environment. Next, we have the simulation result for the heuristic-based approach in the same setup. As evident, all the robots take equal amount of time to reach their goal, which is not seen in the priority-based algorithm. Here we present a comparison between priority and heuristic based algorithm. The heuristic based algorithm is independent of other agents, therefore decentralized, whereas priority based algorithms require path of high priority agents and must be centralized. For this reason, heuristic based path can also be calculated online, while execution for priority based path needs to be calculated offline. In terms of completeness and optimality, both the algorithms are not complete and are approximately optimal. Computation cost of heuristic based algorithm is dependent on map size and can be very high. On the other hand, the priority based algorithms are fast and computationally efficient. Heuristic based algorithm performance is dependent on heuristic parameter tuning, which is not required in priority based algorithm. On the other side, the design of heuristic based algorithm allows it to handle dynamic obstacle, which is not configured in priority based algorithms.
Now here we see the evaluation of our experiments. So our observation states that as expected, the heuristic algorithm takes more computational time than the prioritized algorithm. The difference was expected to grow with the number of the agents, but as discussed in previous slide, it depends on the map size as well. Also, for the path lengths of the two categories, heuristic paths are heavily dependent on the heuristic choice and tuning, and if tuned perfectly, can outperform the priority algorithms as presented in the graph. Now we will talk about the limitations and the conclusions from this project. The heuristic based algorithm serves as a evidence of limitations of the current state-of-the-art priority based algorithms. While priority based algorithm is scalable, it falls short in terms of optimality. On the other hand, the heuristic based algorithm, while scalable, cannot guarantee completeness and is only approximately optimal. These shortcomings have highlighted the need for continued research and development to create an algorithm that is both scalable and optimal while also guaranteeing completeness. Here is our timeline and work distribution for this project. Thank you very much for your patient ears.